Okay, this will be a pretty short video and just continues smoothly from where we left off. We were talking about how the role of pressure can change melting temperatures or boiling temperatures in kind of a qualitative way. We're going to get that into a more analytical way by deriving the Clapeyron equation, which describes the boundary between phases. So here we have now a generic phase diagram just describing two different phases, alpha and beta, with this generic boundary between the two. So if we think about it, what we really want to be able to make predictions of any change of temperature with changes of pressure, right? What we need is dP by dt, right, to describe this boundary, okay, as indicated in the figure. And so to do that, we recognize that at this boundary, the chemical potentials will be equal. In other words, mu of phase alpha at some pressure and temperature will equal mu at phase beta at some pressure and some temperature. And the equation that we want to use to describe those are the fundamental equation of chemical thermodynamics, which says dG equals V dP minus S dt, or, right, using our chemical potential quantity, that's going to be d mu equals Vm dP minus Sm dt. Okay. So we'll now set those two ideas equal to each other, noting that the chemical potential of those phases at the boundary are equal. So I'm going to say molar volume for phase alpha times dP minus molar entropy for phase alpha times dt equals the molar volume for phase beta dP minus molar entropy for phase beta dt. And now we're going to collect like terms with like terms. So I'm going to add the molar entropy for phase beta over to here, and I'm going to subtract the molar entropy for phase alpha, molar volume for phase alpha over to this side. Okay, so it's going to go something like this. We'll have molar entropy for phase beta minus molar entropy for phase alpha, all times dt. And then now that equals the molar volume for phase beta minus the molar volume for phase alpha, all times dP. And so now what we should recognize right away, this quantity Sm beta minus Sm alpha, we will call that delta trans S, so the delta S of the phase transition, times the quantity dt. And that all equals, right, molar volume of beta minus molar volume of alpha gives me the delta trans of the molar volume, so the change in molar volume upon changing phases, times dP. And then collecting like terms, because, right, remember, we want dP by dt to describe this phase boundary, we'll say delta trans S over delta transition V equals dP by dt. And then now noting, because delta S equals delta H divided by T, we're going to change that from entropy to enthalpy, which will be more convenient. Okay, so now that becomes delta transition H over T transition times delta transition V equals dP by dt. And thus, this is our famous Clapeyron equation, which will describe the phase boundary between any phase. And we're going to pick up with that in the next videos and specifically look at that for the solid liquid, the liquid vapor, the solid vapor, and so on. I'll see you then.